welcome everybody to this fantastic event. I would like to especially thank Engineers Without Borders for this co-organization. I am the board leader from FTU, Anna Blekkenberg, and I'm very, very glad that the Norwegian People's Aid asked us to find experts for this fantastic project. So, unfortunately, Innovation Norway hasn't arrived, so I will give the word to Caroline Tut for the first keynote presentation.
Thank you. Thank you. Hi, my name is Tut, and I'm the a senior advisor for innovation for Norwegian People's Aid, Mine Action and Disarmament. I just want to very, very briefly go over what it is that we do at Norwegian People's Aid and why we are running this project that we are now, and what it is that we actually want out of it. And again, apologies that our opening remarks from Innovation Norway could not happen. I believe they're a bit delayed, but our project is funded by Innovation Norway under the Humanitarian Innovation Program, and it is to see if soil sampling can be used in mine action and disarmament work. What is that actually? Well, NPA, we do two main things around the world internationally. We do what's called a development and humanitarian cooperation, and that is essentially assisting local civil society organizations and empowering them. The other main type of work that we do is what we call a mine action and disarmament, and it entails many things. So we have the policy side, we have the risk education, and so on. But one of the main things that we do, or the biggest thing that we do, is what we call land release. What you might know of, think of as land release, what we're calling it now, it's essentially humanitarian demining. It used to be more commonly called just demining or humanitarian demining, but we are calling it land release for this purpose because it entails certain systematic steps. And those steps include non-technical survey, technical survey, and then actual full clearance. And that's the bulk of the work that we do. We clear, in particular, landmines, but not always limited to landmines. It's actually all kinds of explosive ordnance. So ranging from cluster munitions, unexploded ordnance like projectiles, artillery, and so on. After all of our clearance work is done, we do what's called an impact assessment. And it's essentially, we're saying, this land is clear, this land is safe, here's the land back to the community, here's what are you going to be using it for? Are you going to be using it for agriculture? Are you going to be using it for infrastructure, housing? We would like to know, and we would like to help enable you get back on your feet on this land. And this is what we do for many beneficiaries around the world in cooperation with the local authorities there. But going back to land release, it's essentially a systematic process to remove all hazardous materials, explosive remnants of war in a impacted area. So essentially, once our work is done, we have to guarantee that the safety of this land from explosive ordnance. Now, we can't necessarily guarantee the safety from other things, but from explosive ordnance, we have to guarantee that this land is safe. So the first step is what we call a non-technical survey, and it's a evidence-based approach. It's essentially collecting data and mapping an area based on the information that we receive from, let's say, former combatants, from people who live in that area. If there were maps drawn by the former combatants, like what you see on the left, then we try to take that information into account. We talk to local people on the ground. And then what we do is mark and map this area, this hazardous area, through a non-intrusive process. and then we make what is essentially called a polygon, which you'll see on the right. And nowadays, we're using more and more technologies, different technologies to help us in that process, from drone imaging, AI analysis of the land, and so on. But this is essentially a non-intrusive process. So we are not deploying any physical clearance assets on the ground or people on the ground to actually clear this area. Once we have this general area, what's called a suspected hazardous area, then we do what's called technical survey. And technical survey is an intrusive sampling method of these suspected hazardous areas. So we are doing clearance in technical survey, but we're doing clearance in a very limited capacity to find where the actual evidence is. And we are using it in such a way that we can reduce a lot of the full clearance that we have to do, so that we can actually chase down the evidence and make this so-called polygon into a much smaller and more accurate size. Now, why do we do that instead of just going straight to clearance? Well, clearance takes time, it takes resources. It is the most time and labor and resource intensive method of what we do. And so before we deploy all of our assets in full force, we do technical survey. What are these assets? Well, we use manual clearance, which is just essentially people with metal detectors, clearing the area in a very systematic way, removing any of the items that finding any of the suspected items, and then destroying them in situ, usually. We also use dogs to help in that process. So dogs are an enabler of that manual process, but we also use machines as well. Some machines are, let's say, armored excavators, for example, others which are manned or piloted, while others are remote controlled. So as I said before, we don't do full clearance right away. We do non-technical survey and technical survey because full clearance is what takes the most time, takes the most resources. And of course, if you're looking at a country like Ukraine, if we did full clearance of every suspected area, then that would take enormous amounts of time. We're talking about thousands of years. So that's why we have to do our land release work in such a way that is the most efficient, while at the same time guaranteeing the safety of the people who will be using this land. So that's just an overview of what it is that we actually do, and how then will everything fit in when it comes to us trying to survey an area and then also release that area. How will we use soil sampling methods to help either in the survey process or in the impact assessment process? That's something that I want to open up to the floor later on from our colleagues and experts here. So this project, as I mentioned, is funded thanks to Innovation Norway, and the project is called Rapid Soil Test to Protect Civilians and Livelihoods, and it is what I mentioned before. We're trying to look at it from two different angles. Should we look at it from a impact assessment angle, where once we've cleared the land, is the land actually still safe to use, or are there other threats to human health that are remaining in the land? It could be directly from the explosive residue itself, or it could be from other types of contaminants as a result of conflict. We don't know that for sure, and so that's what we're thinking. That's along the lines of what we're thinking. Or we could look at it from another angle to say, are there tools and methodologies, is there the technology available where we can actually make our non-technical survey process more efficient by either scanning or remotely sensing a piece of land that can point out where explosives have been used on that land? So it's an either or, maybe both. We are not yet sure, and that's why there's this market dialogue, that we call it, with private companies, with innovators around the world, but particularly in Norway, to see what is feasible for us to do. So there are essentially two pathways that we are trying to look at. Maybe there might be an overlap of both. Maybe we might have to concentrate on one pathway or another in terms of our innovation work, but we'll see. And as I mentioned before, one pathway is simply looking for the presence of explosives. It doesn't matter if it has any concentrations harmful for human health, but simply remotely sensing the presence of explosives. And that will make our work, our non-technical survey work, a bit more efficient. Or the other pathway is looking at the overall impact after our clearance and how do we measure it? What are we actually even measuring? Like what chemicals are we measuring? In what concentrations are we measuring? And that's a much broader topic that we need to look at as well, that we as NPA do not necessarily have the expertise on either. Or maybe it's something else. We don't know. And what I mean by something else is maybe it's not necessarily the explosives or the residue from the explosives that are causing the most harm. It could be as a result of conflict that there are other chemical contaminants that have been leaked into the soil. Say, for example, if an oil refinery is struck or if a chemical plant is struck and so on. So these are some of the questions that we want to look at. And our next presentation by Kristen, my colleague, will be able to explore some of these questions as well, based on some of the research that we've done so far in Ukraine. Thank you so much.
Thank you, Tut, for a fantastic presentation, very informative. Now we finally have Therese from Innovation Norway here. So we are so grateful that you will talk about this project.
Apologies for being late. And thank you so much for the presentation, Tut. It's really good to be here today. This is the third time that I, as being the head of the Humanitarian Innovation Program, has the pleasure to attend a dialogue such as this between experts of various walks of life that has mine clearance as its topic, as its core. And the other two market dialogues that I have attended both led to multiple partnerships between NPA and various private sector actors that again led to multiple tools that today either already are or will make mine clearance process safer and greener and more efficient. So that's why I'm really excited about being here today, about the dialogue that you guys are having, and I look forward to learning a lot from all of you. Innovation Norway has a humanitarian innovation program that this project is a part of, and our intention is to support, encourage, and de-risk partnerships between the private sector and humanitarian organizations particularly, and often with academia as a partner as well. Our theory of change is that a challenge-based or a needs-based partnership, collaboration between technical experts with complementary expertise, have a great potential to lead to tools and solutions that we need today to solve various societal challenges. And unfortunately, like Tut already explained, the contamination of land due to conflict is a huge societal challenge that we need to address, and we see the potential now to develop even better, efficient, more helpful tools to help us do that. So when we ask humanitarian organizations and private actors and various people with expertise that can be helpful for humanitarian response, why we do not see more collaborations like this. One of the key answers that we get is that we lack places to meet. We lack places where we can have that needed knowledge exchange between people like Tut and everything he knows about mine clearance activities, and people like yourselves with your various expertise from the various areas that you work in. So these market dialogues are a key platform to have that knowledge exchange. And the basis for any sound innovation partnership is a comprehensive understanding of the need, like we've just heard, as well as a good understanding of the opportunities of new solutions. So what are current technological advancements, what are market-ready solutions that can be adopted and deployed, and what are gaps that merit further exploration and that could be met through innovation. So I encourage you all, like you've already done, to listen carefully to what you hear today, to use this opportunity to learn from experts with complementary skills to your own, and to share generously from your own knowledge and experience and your own ideas for how we can more efficiently and effectively release land that has been contaminated due to conflict in the future. So I look forward to seeing what kind of partnerships that will come out of the dialogue that we're having today. Thank you.
Thank you so much, Therese. Now I give the word to Kristin from Norwegian People's Aid.
Thank you. My name is Kristin. I work as a special advisor for Norwegian People's Aid on environment and climate. And I'm here today to talk about a limited study that we did with our partner and environmental researchers from a UK charity about environmental impact from explosive weapons use in southern Ukraine. And when I talk about explosive weapons, it not only means landmines in the ground, but also bombs, shelling, missiles that is being used on infrastructure and communities, and the potential impact from that use on people and the communities. And our core mandate is protecting civilians, but we see more and more that we can't, or protecting the environment is also protecting the civilians. So we need to look more into that, and we're also working to see how we can strengthen the awareness and knowledge about some of these issues and how communities are impacted by war, also in decades after the conflict is over. So I hope that this presentation can give you some background to the discussions later and some of the findings we did. And this is a limited study, and just so you are well aware of that. But due to constraints such as funding and also access, which is difficult for environmental researchers during conflict, and it's challenging to do this kind of research because of security, because of lack of access. But that's something we as the Humanitarian Mine Action Organization can actually provide, because we are present in the area. We have a good dialogue with national authorities, and we are also focusing a lot on security. So very quickly about our work in NPA in Ukraine. We have been present in Ukraine since 2022, and we're working in 3 regions. We're working in the Sumy region in the north, and then in the Kherson and Mykolaiv region in the south. And this study that we did is conducted in the south. As said, we work with our environmental partners, so they are environmental researchers doing the research. And we, as NPA, provided them with our input and the access and necessary logistics to go to the field to actually do the necessary sampling that was needed as well for this project. And it's a limited study, but it provides a snapshot of the current situation. And we conducted 2 field case studies and 3 remote case studies using remote assessment, satellite data, social media, and open sources as well. And there were some limitations to the study. It's very challenging to get any pre-war baseline data. We know that Ukraine is a heavy industrialized country. They have a lot of challenges with pollution even before the war. And we lacked access to prior studies. We had to do extensive preparations to do this. We have to analyze the frontline movements, the fighting intensity, looking at the conflict hotspots and incident locations. And the incidents selected were decided on before, and places we thought that there would actually be an impact as well. And we were supposed to take we collected 55 soil samples and 3 water samples. We were supposed to do more, but because of the landmine contamination and current conflict, ongoing fighting and closeness to the front line, we were not able to access all of the areas that we were planning to. The lab results, they were analyzed in Ukraine with 2 different labs. We had issues with sending them out to get the necessary permissions for that. So this is just showing the area where we, the focus area, we were working in the Snevritska community. You can see it on the map up north there, in the Mykolaiv region, and then further south in the Kherson region. And they were both occupied by the Russians from March to November 2022. They both experienced heavy fighting, and after the occupation, they were both experiencing shelling and missile attacks, and they were both also close to the front line. In addition, the second location in the Kherson region, on the further down on the map here, they were also flooded when the COWI dam breach happened in 2023, when there was an explosion on a dam in Ukraine, and which flooded large areas. I think probably some of you might remember that. And oil spills were also recorded in that area. And you can see the purple color on the map here. That's just an overview of the intensity of the conflict. So this is just an overview of the soil samples we collected and the findings. And I'm sorry if it's a bit small for you to see, but we found elevated levels of heavy metals there: zinc, nickel, vanadium, lead, and copper. Selenium and arsenic concentrations exceeded the background values and Ukraine's legal limits. And phosphorus and sulfur levels as well were notably higher in most cases. So this is just to show you a few of the areas where we did collect the soil samples. And near the railway station, for instance, that was destroyed by shelling, the soil samples relieved excessive concentrations of lead, arsenic, and sulfur. In the riverside and residential areas that were occupied by the Russians, it also showed elevated concentrations and contamination. And many of the samples also contained benzopyrene, which is a harmful chemical that can increase the risk of cancer. And this is likely due to fires involving plastics or fire coming from the weapons that have been used in that area. And this is the overview of the sampling we did in the other region, in Kherson region. And you can see on the map here with the green or blue that you can see areas that have been flooded, just to show how they were flooded by the dam breach that happened in 2023. And we also found evidence here for petroleum hydrocarbons in all the 8 samples we took where we suspected to find or where it had been oil spills. We also found elevated concentrations of zinc and nickel, manganese, cadmium, and other metals, which is likely to indicate that the floodwaters from the dam mobilized pollutions from earlier, from different industrial sites in the area that had been damaged in the war. And the water samples, although they were very limited, showed hydrocarbons and heavy metals exceeding drinking water standards by tens to hundreds of times. So it was very unsafe for consumption. Just again to show a few of the areas where we took the samples, and you can see some of them what they were showing here. And on the right there, you have just samples on the boreholes. And luckily, the community were aware that the water was unsafe to drink, so it was just used for household, not drinking. And I just want to quickly also show you one of the remote case studies, just as a background. I will go through it a bit quickly, but this is something where we would have liked to do a case study, but we didn't have the access. But this shows one of the oil pumping stations in the area. You can see it's in the midst of an agriculture area, and to the top left there, you have the original satellite photo or overview photo of the oil pumping station. And then in 2022, one of the oil tanks was attacked and bombed. And you can see on the second photo there, a large plume, which was about 2.5 kilometers of black thick smoke. And on the third and fourth photo there, it also shows the damage to pipeline in the area. And then again, a few months later, and the pumping station was attacked again, and 2 more oil tanks were bombed. And the Ukrainian authorities did some limited soil sampling in the area, which they estimated to be approximately 33,000 square meters, or like 5 football fields. And their soil samples there showed levels 35 times higher than permitted for hydrocarbons in that area. And based on the remote assessments that our partner did, we also expect the area to be contaminated with heavy metals and possibly also chemicals from the fire as well. So a few of the key findings, I won't go through them all, but I think the main finding was that although this was a limited study, we did document the use of explosive, or that the use of explosive weapons impacted the physical, chemical, and potentially biological property of the soil in the area where we tested. We found a considerable level of pollution through the sampling we did, including heavy metals, including hydrocarbons, exceeding permissible levels in Ukraine, according to their standards. However, we did not assess them to be of any immediate risks to the people living there. The water samples, on the other hand, indicated significant levels of contamination in the groundwater, not safe to drink at all, but as I said, people were quite aware about that, which was very good. We also documented extensive damage to critical infrastructure, as energy and water and other industrial and agriculture infrastructure as well. So in addition to causing power and water interruptions, this can also impact the soil and water in general and increase the risk of the spread of waterborne diseases as well. We also documented how the dam breach had carried existing pollution from the conflict into new areas. And we are pretty sure of this because the pollution we found were in areas that were mostly used for agriculture and didn't have any significant local pollution before the flooding. And in addition to threatening potentially the health of people, the explosive use and contamination made damage to agriculture areas. We saw evidence of landscapes fires and harm on irrigation structures that could impact the local food security and the livelihoods. And we did not specifically look into how this contamination could go into the food chain in any way. That was not the scope of this study. And besides, many of the areas are contaminated with landmines and other types of weapons, which makes it difficult to actually access the area, do the necessarily data collection which is needed, and also do any environmental management or remediation as well. So the main recommendation from the study we did was that there is a need to expand the sampling in the area we were working to clarify potential risks in affected communities. And this will help prevent further contamination and possibly then identify protective measures for people and ecosystems. And if I lived in one of these communities with my family and my kids, I would have wanted to know how this pollution potentially could impact me and my family immediately, but also in the longer run. And I think collecting more data like this would help us to work with the communities. It can empower the communities. In some cases, it can also take away their worry. But in other cases, it can also demonstrate that there is a need for more data collection and research and longer-term monitoring and assistance. And then I think I'm over time now, so yeah, no, it's okay. So a few more of the recommendations. Won't go into them in detail, but I think it's a need to undertake more survey and mine clearance. And of course, we know from before that that explosives in the ground can also leak heavy metals and toxins. We've seen many places as well, especially if you have contamination close to the close to the river that the landmines can flood, they can move as well. And there is a need to have, or I think there is a need to document this better and have a greater awareness and understanding of the potential environmental impact, and make sure that we integrate environmental assessments and data collection into post-conflict recovery and reconstruction. And I think what we are working for in Norwegian People's Aid as well, on a more political and international level, is to bring up this awareness and strengthen the international law, both protecting civilians and the environment. So I think that just to summarize, we did, here you can find the link to our report, and we did document that pollution was caused by the use of explosive weapons in the war. And this was just a snapshot study, as said. And as you see, there are several issues that can cause pollution in conflict. And I hope that this presentation and some of these findings we did can give some background to some of the discussions that we have later today. And I think this is more and more important as we know that we have a current, we have a climate, and we have a nature crisis. And we need to integrate these considerations better into the planning of our work and supporting communities in a post-conflict setting and in reconstruction and rebuilding as well. So we welcome any feedback to this study, and we are interested in doing similar collaborations. So if you have a look at the report, please don't hesitate to get in touch. Thank you.
Thank you so much, Kristin, and it's a real honor for us in FTU to be able to help you with this fantastic innovation project. Now we will present the next speaker, Erik Joner, Head of Research at NIBIO. He's researched for 30 years on poison in soil or something.
More or less. Thank you. My background is I'm a soil scientist and a soil microbiologist, and I've been working, as it was said, on different types of soil pollution. Started out with fallout from Chernobyl, actually, cesium in Norway, and then moving on to heavy metals, to organic pollutants, to nanoparticles, to microplastics, to various types of organic pollutants. I've been challenged to say a little bit about what bioremediation and biochar can do for cleaning up soils. We've been working with both of these in different projects. Whoops, let's see here. That was not the right way. Okay. Just as a general background on soil contamination, I don't see that very well. The problem with contaminated soil in an agricultural context is, of course, that it can these contaminants can be taken up into plants, and as we heard also, leak out into water, drainage water, and groundwater. When we talk about pollutants in soil, we talk about organic pollutants in the context of PBT, so persistence and bioaccumulation and toxicity. We need to at least have two of these to be of concern. So if organic contaminants are degraded relatively fast, then it's usually not much of a problem, and that's why breaking them down through remediation processes can be a solution. What happens to contaminants in soil is that their bioavailability is modified with time due to the contact with soil. And this also affects then the transfer of these contaminants to plants. So point source contamination is usually a small problem. We can delimit a spill of oil or something, a car that petroleum spill from cars, from tanks, or from petrol stations and other things. But if the volumes are large and the areas concerned are great, then of course it will be more of concern for public health. Exposure and risks are based on those things. So organic pollutants, we are either able, as I said, to treat by degradation, so bioremediation, using biological processes to break down these contaminants, or by immobilization, which means we either use the soil as it is, or we stimulate it by adding some sort of soil amendment to enhance adsorption in soil, so that we reduce mobility, that means transfer to the plants or transfer to groundwater. Bioremediation is a general term for biological breakdown of organic pollutants, and it's basically used in soil. You can use it in waste also. You can collect organic material and treat it biologically to reduce the amounts of pollutants in it. But basically, it's about soil. Phytoremediation is a kind of a subcategory of bioremediation where you use plants. Phyto is plants then. And the thing about plants is that they enrich the soil with carbon, with easily available nutrients for microorganisms living in the soil. Roots are actually leaking what we call the root exudates into the soil. It's like a flow of sugar, constituting maybe as much as 10% of photosynthesis, is directly leaked into soil to stimulate soil biota, so that these bacteria and fungi can mobilize nutrients in soil for the plant. It's a kind of a symbiosis, but it's also a process that enhances general microbial activity in soil, and that can have an effect on the breakdown of contaminants. This is sometimes known as co-metabolism, if it's a sort of a primary carbon source that is driving the degradation of a secondary source like organic contaminants. This is a kind of root zone degradation, but you can also have a type of phytoremediation where the contaminants are actually absorbed by plants. This can work both with heavy metals and with organics, and then in the case of organics, they will be metabolized by the metabolic system of the plant, while for metals it's sequestered in the plants, and you need to treat the plants as some sort of waste depending on the concentrations. In general, soil is a very favorable environment for degradation. That is what soil is about. If soil wasn't an efficient biogeochemical reactor for breaking down organic matter, we would be at least up to our waist in insect shells and leaves and plant debris. So the reason why we don't walk around in debris is because soil is taking care of all sorts of organic waste, also anthropogenic waste like we are producing in large amounts in our days. This is because soil is a very porous and favorable environment when it comes to oxygen availability, suitable pH, suitable moisture, and this extra input of organic carbon that boosts microbial activity. In addition, soil contains an enormous array of very capable microorganisms that can degrade almost anything. If something can be degraded in this world, it can be degraded in soil. It's as much as almost 60% of the biodiversity on Earth is found in soil. So there is an enormous metabolic capacity there. But soil biota are usually starving. They are dormant, so stimulating them is a good idea to make things happen faster. The other way of doing remediation is sorption, meaning you immobilize, this can be organics or metals, to avoid plant uptake or avoid leaching into water. So soils are composed of mineral particles and soil organic matter, and these two main fractions have different properties when it comes to adsorbing pollutants. Organic matter typically contains hydrophobic domains which can adsorb hydrophobic contaminants like oil or PAHs and so on, while clay, but also other domains of soil organic matter, contains charged domains which can adsorb metals and charged organic molecules. And when contaminants come into soil or come in contact with soil, this adsorption is the adsorption strength is usually increasing over time. This is what we call aging. So as time goes by, contaminants in soil usually get less bioavailable. It's something that saves us in many contexts. Then, of course, there is the possibility to add additional sorbents to soil. Particularly in sandy soil, you can add things that replace clay or that mimic the effects of clay, and one of these things are biochar. Biochar is charcoal, basically. You take some organic matter. It can be forest debris, it can be straw, it can be algae from the sea, whatever. You pyrolyze it. It means you heat them to above 400 degrees without oxygen availability, which basically creates a carbonaceous material, which often has a very high porosity, and this porosity is key to this adsorption technology. So the biochar, like soil organic matter, contains both charged and hydrophobic domains, and it has a very high capacity to adsorb some type of pollutants. For heavy metals, it's not the most efficient. I've been working for 7 years on the area of Alun Shale around Hamar and Stange, which contains a lot of cadmium, arsenic, uranium even, looking at if biochar can actually immobilize heavy metals in those soils, because they accumulate in plants at levels which are sometimes preventing their sale in shops. There we didn't find very promising effects of biochar when it comes to adsorption of metals, but then again we only tested two different types, and biochar is not a single thing. Biochar has properties which depends very much on its original material and its pyrolysis conditions. So biochar can be tuned, it can even be activated by treating it after the pyrolysis. So on the other hand side, for example, these fluorinated pollutants that we know as forever chemicals, the PFAS, they are adsorbed very strongly by biochar, and PAHs are adsorbed strongly by biochar. So for organic contaminants, biochar is maybe a way forward. Unfortunately, biochar is quite expensive, and not many people produce it in high amounts, so it's also a question of economy. On the other hand side, the biochar has secondary effects which are very positive for what we call soil health. So it's a thing that usually is good to add to most soils. Okay, I'll stop there. Just showing an example of using biochar on a slightly larger scale in an urban environment, using what they call the Stockholm soil mix, which is consisting of a large proportion of biochar. So I think I'll stop there. Thank you.
Thank you so much, Erik. The next speaker will be Hege Vågen from Sweco. Thank you.
Son? Yeah, hello. I'm Hege, and I work as an environmental geologist at Sweco. So I work daily with quite a lot of different projects with contamination, different kind of contamination issues. And the contamination situation is severe and so vast in Ukraine, it can almost be like hard to wrap your heads around, right? It's hard to know where to begin. And I wasn't 100% sure what I was going to talk about when I first was invited to come here, but I thought I could say a little bit about the general steps that we follow when we work with contaminated land, and a little bit about some tools that I found very helpful in my daily work life, and maybe that some of these tools can be adapted and maybe implemented in the big process of cleaning up agricultural fields of Ukraine. And when I was thinking a little bit about these tools, I actually also saw that when you had some key discussion points that you said you wanted to go through, and some of these tools actually help answer out the questions of what role can communities and local stakeholders play in monitoring and managing contaminated sites, and how can test results be effectively integrated into land use planning and remediation strategies. So just very quickly about the general steps. When we have a contaminated, let's say, an agricultural field, we would always start with a desk study or like a remote study, as was talked about earlier. You try and get as much information on the site to try and answer out the question of what contaminants do we expect here. You then would often follow up with field work, a field assessment to find out how high are the concentrations, how bad is it actually. And that would be followed on with trying to answer out what are acceptable concentrations in the soil and water with respect to the planned end use of this agricultural field. And based on that, you have like site-specific remediation strategy that is good for that field, and with the goal of producing safe food at the end. So the tools I'm going to talk about, one of them is in step 1 and in step 3. So a little bit about step 1 first. Well, what contaminants do we expect in the area? The sources from the war are going to be a lot. This is just like a top of the iceberg, I'm sure, of all different sources and what kind of contaminants that we can expect. And also so much information from where we can find information, what's been going on in this area. And you need to like ask yourselves, how can we gather all this information together for the people who are going to do the work of prioritization, planning, and conducting the actual cleanup process. And in Norway, we have something called a contamination database that we use. So let me just... I've taken a little screenshot here from Oslo, and you see all these little triangles are registered contaminated spots, and I have zoomed in from a little area up in Lillestrøm here, and you see it's all color-coded, and they have different meanings. For example, purple means that we suspect that there is contaminated land there. The red say that here we've already done an investigation. The contamination is not acceptable. Action is needed in the red areas. In the yellow areas, we have already done an investigation, but the contamination levels are acceptable with the current land use. And this database is available for everyone. And what's really great is that you can click on each of these polygons, and site-specific information will come up. Like this is not a very good example, but one locality you can see what's reporting and concentrations and whatever. It's a tool that is used by environmental authorities in Norway, about us environmental geologists that work for projects. And I was thinking it's a very good tool to share knowledge about a land. And it's a good tool for also to share knowledge between local communities and local stakeholders. And yeah, I was thinking a tool like this must be helpful in the process of cleaning up Ukraine. And actually did a little research online, and I found out that a Ukrainian environmental group is already working with this, trying to collect data and presenting some sort of where to begin, because as I mentioned, the cleanup process is really vast and it's going to take a long time, many hundred years to finish, and it is important that the data that we have now available is stored somewhere for the future with knowledge, and it's going to disappear with time. I think also it's important to mention that the process of prioritizing where to begin on this big cleanup is going to be difficult. So maybe this sort of tool could help with that. Back over to the step 3. That was a little bit about like a tool of database that we found very helpful in our work. And over to the step 3, where you have, what that is contaminated. You've done step 1 and 2, and now you want to ask what are the acceptable concentrations in the soil with respect to the end use. I think the process of deciding what the future agricultural end use is going to be difficult without any good guidelines for the people who are working, and on the ground they're going to be looking for guidelines and help to answer out these questions. And I thought I could just say a little bit about what we use in Norway. We have something called tilstandsklasser, and it is just a short cutout here, but we have a long list of like common contaminants, and then it's classified into from good concentrations until very bad concentrations. And this system is quite useful in like making a lot of concentrational data a little bit more easy to work with. And it's also these kinds of classifications are used in advising people with what their the end use of area should be. In Norway, for example, if you're going to have a nursery or school or housing, it's quite strict with what you can have in the topsoils. You have to be either in like a very good or good concentration classes. I'm just showing you the heavy metals here, but the list is very long. And then you have, for example, infrastructure, or let's say a shopping mall. Maybe it's not so sensitive area, and you can tolerate a little bit more contamination. So, for example, if I'm working on a project with heavy metal concentrations that are up in the red area, maybe it wouldn't be a very good advice to say that you should plan to build a school here in the future. So it's kind of, that's how we use it, and it's very useful in that way. And I just wanted to ask if a system like this can be adapted to make it easier for Ukrainians to evaluate what kind of crops they should grow on their contaminated land. I know that there's a different contaminant uptake in different foods, and I know there is a lot of research available and knowledge available about the contaminant uptake in food, and can this be like made simple and easy for people to use in Ukraine of information. So that was more like an idea I was going to share, and I think I will stop there. And I'm really excited to see what comes out from the discussion of saving Ukraine from war poison. So thank you.
Thank you so much, Hege. A really interesting presentation. We are so grateful that Norwegian People's Aid has actually chosen to use Norwegian experts in this innovation project. So I'm so grateful that all of you here were positive to contribute to this event. So now I will present Marian from SINTEF. She's a research manager for smart sensors.
Thank you. Hello, everyone. Thank you, and thank you for the invitation to come here, Anna. I'm going to give a presentation about different sensors we develop in SINTEF. I work in a department called Smart Sensors and Microsystems, and we develop sensors across a large range of areas. So we develop different types of sensors, whether they use acoustics or optics or analog sensors. We also work on miniaturization, like MEMS design. We have production of these types of technology in our Minilab facilities. We develop also instrumentation, software packaging, so that we bring a component up to a system level that works for an end user's need. And of course, we have also the communication and the analytics, the AI, the machine learning that goes on top of that. So I'm representing 100 researchers here, so I won't be able to answer every question about every sensor. I work personally with optics, but we do cover a broad range of technology, and this could be relevant. And the knowledge that we have is broad, and we are also technology provider neutral. That is our stance generally in these types of projects. So our goal would not be to sell our product, it would be to find what's best for the application. So just to explain, we work from the fundamental level physics, we simulate real world situations. This is how we research. We develop technology that's neutral to vendors. We do early prototyping, so we would generally take a measurement challenge. We would get out into the field as soon as possible, so we test in the lab, but we need to get out of the lab quite quickly if we're going to make sure something will work or it is useful. And then we understand what's affecting our measurement. Why isn't it working? Why is it wrong? Is it correct? And analyzing that and just making it useful. So this is an example of a simulation. This is an example of technology that we have developed down by the Oslo Fjord and all the way to measuring red tuna in Spain. So we get it out of the lab, and that's an important aspect of our work. For us to work in projects, you have to combine hardware, analytics, and domain knowledge. So we don't often have the domain knowledge. That would be like Eric on the soil science in this application. But we would come with the stuff that will make the sensor possible. So the best projects for us is where you combine these together, and then you have an infrastructure underneath which allows you to build the sensors or build the system that you need. So that's just a little introduction of how we work and what we can contribute. So when it comes to measurements for soil, I've divided them into 3 types of areas. The top one being large area scanning. I mean, you've called it different things, but this idea of taking larger areas and getting an impression of it. And I've measured some technologies. I'll go into the details of the methodologies in the next few slides. Then there's handheld and portable. What can you take out in the field near to your sample, but without needing too much sample preparation. So when I say handheld portable, I mean something that, like, you have a gun, a handheld gun, for example, and you point it at something and you get a measurement. And then you have a lab in the field, which is like bringing a lab to the field. So there it's probably necessary to do some kind of extraction to release what you want to measure into a liquid, for example, form, so that you can do the measurement. So it's like a more cumbersome process, but it'll give you often very accurate results. So these have different levels of preparation. They cover different areas. So the combination is often what you're going to need, and you have to prioritize what is it that you need to do first. I mean, large scanning, area scanning might be the first step, so that you start, because it's such a large country that we don't actually know where to start, and maybe that's the priority for this project initially. But we should always be looking towards, okay, you find a hotspot, what do you do then? Then you need something more like the second 2 measurements. Just talking about LIBS and XRF. LIBS is laser-induced breakdown spectroscopy. You don't need to understand any of these, but XRF is X-ray fluorescence. So these two methods are both possible to get in gun format. They're like a handheld pistol, but also, I mean, LIBS is on Mars. It's used to point and shoot at rocks to discover what their composition is. Raman is also used, but this idea of measuring metals, LIBS has an advantage over XRF in that it can measure the lighter, the lower atomic weight elements. What it does is you focus a laser, you cause a tiny explosion, and you break the molecules into their elements. And you can measure then these elements and get an indication of what is in the soil. And these are good for this coming out into the field where you want to measure a sample. You might have to compress it a little bit, but you don't need to extract it using water or acid or anything like that. You just need to point and measure. And I've just given some examples for inspiration without knowing if any. I haven't used some of these. We've used LibScan once, but I haven't evaluated these for this application. It's just a suggestion of types of technology. And then you have near-infrared technology, which is a type of spectroscopy at wavelengths a little bit longer than the visible. This can be lower in cost, and it would be suitable for this large area scanning. So this is something you could mount on a drone, fly around, and get an impression of some chemical composition. So it could be used for TNT, RDX, HMX, and hydrocarbons. So HiSpecs is a Norwegian product developed by Norsk Elektro-Optikk. This is a report I found of theirs online where they've done some tests on explosive contaminants at a shooting range, and then they have imaged it using this hyperspectral camera. So it's a camera that also gives you wavelengths, not just color, but wavelengths up in the near infrared. But you can see there's signatures, there's fingerprint marks, grass has its own signature, TNT, HMX. You could find, this is a high-level, high-performance system, quite expensive, but you could make something based on just a simpler camera and adding filters, or you can highlight some wavelengths. This will give you all wavelengths, so there's always a possibility to go down in cost or simplify the system. And we've done work like that, for example, in ice detection for road conditions, determining if there's ice and the driving conditions, using near cameras and applying filters to simulate what this higher cost kind of system would do. So this could be a method. It's much lower in cost than LIBS and XRF, and it would be suitable for mounting on a drone and flying close to the soil and getting measurements. And then you have other methods like mass spectroscopy, which are much more expensive, but you will get much better results. They're highly accurate. This Torion is a kind of a suitcase system, but you generally have a little kit to prepare your samples. You have to introduce the sample to the system and allow it to do its work. It works on ionization of the compounds. Much more expensive, but so accurate that, I mean, it would be used in security and drug court cases, for example. So it's used to really give details of what you need to measure at an accurate concentration, if that's what's needed. So it's, again, what accuracy do you need, and what price category is suitable? Do you want people who are able to do this without being trained in any way? So there's a lot of questions to ask, and how the system would be used as well. But this would require following very accurate steps to achieve the accuracy. Drones, of course, is very relevant here because of the large area scanning idea. And you can think three types of sensors. This near that I measured, which you could get some chemical information if you look at the near infrared wavelengths. There's also ground penetration radar, like this orange one here, which could be mounted on the bottom of a drone. And that can give you depth through the soil, like a 3D slice, measuring if there's metal in the soil, because it would have a different density. And then you'd have thermal imaging. This can disturb the soil heat absorption and emission properties, so you could maybe see something. You could combine near imaging and thermal imaging, for example, to get both perspectives because they measure different things. And then you can also, like as I mentioned, a Norwegian company here, Biodrone AS, they've actually done some imagery analysis for mine detection, but they've actually been looking at visible images where you can see that it's a mine in the photograph, not actually measuring, you know that one, not actually measuring the chemical composition of it. So we have a lot of experience developing sensors for mobile autonomous platforms, whether they're flying or driving, navigating and sensing. You can navigate first, then sense. We've done quite a lot of that in SINTEF. And we have, not in our direct department, but in another department working with geophysics, or they have a geo-drone platform as well. And of course, drones can be combined with satellite data. So you can also think you've got historical satellite images, then you create a new image with your drone, build up a database. We have done work where we've combined interviews with people and user manuals like text and using ChatGPT and audio, analysis of audios, where you combine all those sources with imagery to extract information. So the idea of interviewing people, we have people in SINTEF working on this kind of interviewing and extracting information from that as well. And also behavior of people can also give you information as well. So that's just another possible way of thinking about it. And then going forward, thinking kind of more future direction, is this is work that Minilab, which is the micro-nano lab in SINTEF, they're working on developing these really enhanced structures. So up on top you have nanostructures to increase the signal intensity and information. And they are working on pesticides and water, so using tiny microfluidic chips. And you have this gives you the possibility of in the future having something lower in cost that will be able to be used quite quickly and cost very little for people in the field. This would be suitable for water samples. And the one on the bottom here is a plasma on a chip, which is similar to LIBS. LIBS creates a plasma. And this is a EU project measuring the breath of people who have pulmonary diseases, because they release different molecules in their breath, and you would release the breath in here. It causes a plasma with its own signature. So if there's volatile organic compounds, for example, or PAHs that you're interested in, these kind of methods could be used for that. So without knowing what the application is yet, this is just giving you an idea of what could be gone through. And we would have to start with a kind of an analysis and getting real soil samples. That's how in my head we would start with something like this, is receiving samples, getting knowledge from a soil scientist and building up knowledge about what concentrations we're talking about, which method sees what we need to see, and what could be scanning if that's what the priority is. So this collaboration would be necessary. It's a much better type of project. And then just in terms of questions that we would often ask, is soil preparation acceptable, like extracting with metals or with acid, what degree of accuracy is required? Are you looking for a threshold, or do you need to know exactly the concentration? Assuming large spatial variation, do we just have to decide, yes, drones have to be part of the toolbox? And then what would a drone be looking for? Is explosive ordnance generally found at low? Exploded, so if it's unexploded, it's concentrated, but how low concentrations do you get when it's after it's exploded? And if someone who knows this was looking at images, how would they identify hotspots? So this kind of domain knowledge is important. What would they be looking for in an image? And how deep into the soil are the contaminants likely to be found? So some of these methods only measure on the surface, and the radar will go down under the surface, but a lot of them stay at the surface. So you'll get a surface measurement, and is that enough? So these are just some trigger questions to see if you have any thoughts on that as well. So that's all from me. Thank you.
Thank you so much. I wonder, we are a bit ahead of the schedule. Should we take a 5 minutes pause now? What do you think? Or, yeah, 5 minutes pause, and then we continue with the panel discussions.
Yeah, the next session, I will be moderating a panel with some of the presenters that went, as well as 2 other colleagues who haven't had a chance to talk yet. So I would like to introduce, and please forgive me if I butcher any Norwegian names, but Harald Bjornstad, he's a senior advisor at Forsvarsbygg. Harald, please, welcome. And Ingrid Jelsteland, head of discipline at COWI. And of course, our previous speakers, Marion, Eric, Hege, and Kristen. So we are hoping for this to be a more an open discussion, but I would like to start off by just asking a few leading questions, especially for our two colleagues who have not yet spoken. So with those opening questions, I'll then open up the questions to the floor, as well as we have two questions online as well from some of our participants who are tuning in. So starting off, so the first question for Harald then is, we understand that the Norwegian military does similar work in terms of range clearance or clearance of explosive ordnance in shooting ranges, a little similar to what we do in terms of clearance of conflict areas, areas where there's explosive ordnance contamination. So what can you tell us about what are some of the remediation efforts that you do? What are some of the explosive compounds or other compounds you test for? And what are the procedures that you would do? Like, for example, how do you first test for military style type explosives like TNT and RDX? Do you test for other things? And as well as what are the follow-on actions afterwards?
Mm-hmm. Okay, thank you. Yes, when we go out in the field, we have experts taking care of the ordinances, and after that we can come in as field experts and taking samples. And the first thing we are normally doing, we are using what we just presented here, using the X-ray handheld instrument that can we can find heavy metals in just a few seconds. And then we can take some samples and send them to the lab afterwards to check out for explosives like TNT and RDX. And we do not normally find so much explosives because we don't have so many ordinances. You have here and then there are some of them, but we have dump sites of bombs from Second World War and later on for testing grounds, and there we can find some of the TNTs. And we have very many chemical compounds and that are degraded from TNTs, and we have a list that is sent to the lab, and they will check all of these chemical compounds that we are found in the explosives.
And may I perhaps ask then, the chemical compounds that you do search and test for, were they in concentrations that would have health effects or environmental effects, and how would those then be dealt with?
Mm-hmm. Yeah, some of them, we have some standards we are looking after for TNTs. We don't have for standards that we have from the Norwegian Research Defense Institute. They have made some standards. That's lots of them are from the US because there's much more explosive and shooting fields and ground there. And so we look upon that, and then we see what's acceptable in, for example, in drinking water, what can leak out. And what we have found so far is that we have it's not a big issue in Norway, but in comparison to Ukraine, it could be we can multiply it 1,000 times, and then it could be a big issue there, especially in the groundwater, I think. Yeah.
Thank you. I think moving on, just a question then, the next question for Ingrid. I understand that your organization, your firm, is quite heavily involved in the assessment and of soil and testing for various types of soil contamination. I'm just wondering, what are some of the latest tools that your organization have been using in order to do the work that you're doing, and how far the technology has come in terms of what you're able to do?
Well, thank you for inviting me first. First of all, I believe that before we can rebuild, we need to make sure that it's safe to live and farm in these areas. So what we do when it comes to tools and technologies, I think it's already been mentioned several times, but we go onto the contaminated sites. We take soil samples and we send them to the laboratory for analysis. We also do field testing with the X-ray technology. That's also been mentioned here. And we've used it for cleaning up old shooting ranges in Norway. When it comes to future solutions, I think drones is essential here. This is large areas that needs to be investigated. So drones, together with all of the tools and technologies we have with satellite images, normal field soil samples, and also the X-ray technology. We're able to detect all kinds of chemical compounds. I think the X-ray technology and also different technologies mentioned by SINTEF, you have on-site field testing of heavy metals and organic compounds. But with traditional testing and sending soil samples to the laboratories, you can have all the compounds tested for. I think it's also important to look at water and not just soil, because the contamination will be spread to different waterways, and water will be used for irrigation of the farmlands. So testing for more than just soil would also be important.
Thank you. Perhaps I can move on to questions both from the audience and online. We only have 2 questions online, so perhaps we'll start there. First question is actually to NPA, so perhaps I'll try to answer that, maybe with help from my colleague Kristen. So the first question is, does the phosphorus contamination come from white phosphorus use? And should white phosphorus be banned? What is the effect on people, plants, animals? So lots of questions there. Maybe I'll try to break it down one by one. Does the phosphorus contamination come from white phosphorus use? To my knowledge, and maybe perhaps Kristen can elaborate, to my knowledge, we don't know, because phosphorus is also an agricultural chemical. So to my knowledge, we don't know whether the white phosphorus itself that's used in conflict, in war, if that's left in the soil, whether it's from the conflict itself or whether it's from pre-existing agricultural use. So inconclusive as far as I know. But what is white phosphorus itself? Yeah, it's used as a smoke in military settings. So you use the smoke to conceal your own movements and so on. But there's been some creative uses by certain state actors that are contrary to, I would say, humanitarian law. In which case, the smoke itself, while it does produce smoke, the material itself does produce smoke, it also burns very hot with exposure to oxygen. And so that has been used in some instances as an incendiary weapon, and a lot of the times incendiary weapon against civilians. So can and should it be banned? Yes, that is the position that our policy team is trying to articulate as well, and we're still working on the nuances of that position. But as far as a weapon or a tool used against civilian populations, that of course is unacceptable to us as a humanitarian organization. What white phosphorus does, or as I explained, is it can burn, and so what's left in the soil, usually if it's completely buried with no oxygen, then it won't necessarily burn. But whether those compounds then leach into other forms or into either the soil itself or the groundwater, that we don't know, and we as a humanitarian organization that's focused on clearance of munitions, we don't have enough data and information on. But what we do is if we find, let's say, a white phosphorus piece of ammunition, the commonly accepted procedure for us is to actually destroy it in the most destructive way possible so that all of it can be vented and released. And burnt off, essentially. So we try to use as much explosive as we can, usually to break open a white phosphorus container, for example, and so that all of that can be burnt off. What are the long-term implications of that? That is also something that we need to look at more as well. But that's typically in EOD, the explosive ordnance disposal, that's the commonly accepted procedure. And there are various ways to go about it, of course, but that's, the general concept is you want to burn it off as much as you can.
Mm-hmm. Can I have a little comment there?
Yes.
Because it's an old study in Canadian where they have used white phosphor bombs and spread particles over wetlands, and it's very poisoned. And many ducks and birds living in the wetland, they died because of white phosphorus in small particles. They thought it was food, so they ate it. So it's a quite problem. I mean, now it has been used in Ukraine on both sides of the parties. Yeah.
I'll just comment quickly in regards to the study we did in Ukraine. We didn't have any bomb data or information if that was white phosphorus munitions were used in that area. And I think that's often also the case, also for other types of munitions, such as containing depleted uranium, for instance. So based on where the phosphorus came from, we didn't look into that because we didn't have the information.
Thank you. Maybe going over to the next question. Can you identify where mines explosives are in soil with LIBS and other technologies? And can that replace deminers or help operations? How accurate is it? Well, that's part of what we're trying to learn about and identify and discover as well, is can we use some of the technologies that are available now to maybe not identify exactly where a mine is, but a general area of where mines have been laid or where explosives have been detonated or in the ground itself. Can that replace deminers? From my experience, the short answer is no, because you're still going to have someone go and find and destroy or remove the threat that's on the ground, whether it's as I mentioned, with just the deminers themselves, with just the personnel, or with the help of dogs and machines, that's still going to have to be done in some way, shape, or form. But can it help? Absolutely. If, as I said, what we do in that land release process is we try to narrow down information step by step. So, the first step, when we do non-technical survey, because it's a non-intrusive process, we're essentially mapping out larger areas of land based on direct and indirect evidence, based on the information that's provided to us. We make I don't want to use the phrase educated guess, but we make certain assumptions based on the information that's available to us in order to map out and then mark from a distance an area that we believe is contaminated with explosive ordnance, with mines, etc., etc. If we were to spend all of our time clearing that large area, then that is going to be a huge ordeal in terms of the time and the resources required to clear that area. So that's why then we do intrusive sampling, or what we call a technical survey, in order to actually confirm whether these reported bits of evidence are true or not, and then narrow down step by step where the actual mines and explosive ordnance are, and then we can actually do the full clearance of those very specific, what we call confirmed hazardous areas. So if we are able to then, off the bat, identify confirmed hazardous areas, or have more evidence in order to identify confirmed hazardous areas, then of course that whole process becomes a lot more efficient, a lot more accurate, and so on. So yes, it will help in operations, but of course you will still need someone to actually go and search and destroy the items once we identify the general area that they're located. How accurate is it? All these technologies, I cannot say because I'm not an expert, nor am I familiar with all these technologies that are available. So perhaps I can give the floor to Marion.
Yeah, I can comment on that. I think the biggest challenge with LIBS is that it is a point measurement. So it will measure, it is a laser being focused on a small point. So the problem with soil is that it's very heterogeneous. That one point mightn't be representative of another point 1 meter away, or even half a meter, or even less, you were saying. It's very heterogeneous. So the biggest challenge there is covering the area. So that is a disadvantage at the offset. But then that's why you need to combine it with kind of imaging systems that will give you a broader visibility. But the LIBS will give you a broad range of metals, for example, including the lighter metals. But then, as we were talking about in the break, it's not necessary that all metals are contaminants for plants, because plants absorb often, like plant available nutrients. They are the ones that are dissolved in water. So what is available to the plant and what's absorbed by the plant, it's probably a good idea to know, so that we're actually measuring the things that we need to measure and not measuring everything. So, but it can be quite accurate. You can build models, but the soil itself is very variable underneath the measurement. So it has to be taken into account, and it can be interfering with the metal detection.
Thank you.
I have a question. Yeah. So maybe this goes to both SINTEF and NIBIO, because from your presentation, we saw that we're dealing with all the chemicals you can think of, both from war activities, but also from industry being affected. And you have pollutants that affect local areas, and also those that are spread over a wide area. So one of the advantages with sending samples to a laboratory is that you can analyze for a range of compounds. But with the in situ, both technologies and also remediation techniques, how is it addressed that you have so many different compounds and not just one or two?
For heavy metals, you can of course analyze a lot of them at the same time, and for organic contaminants, you would have to go for some sort of targeted approach. You can do non-target analysis, of course, but if we're talking mainly explosives or hydrocarbon contamination, you have some you can call them sentinels, or you can pick out certain that are indicators of a wider range. And of course you can do this on soil, but sometimes it would be even smarter to try to do it on water, because if you have a sort of a watershed that drains into a stream or a river, preferably smaller streams, you can sort of say that, okay, within this watershed there is nothing mobile of concern, because if things are taken up into plants, they're usually also leaking into the water. So this is also something that NIBIO has a lot of experience with, monitoring of drainage water from watersheds, agricultural watersheds. And there you can do sort of proportional water sampling so that you get you can correct for precipitation intensity or from thawing events in spring and so on. So these are also potential monitoring methods, looking at the water samples draining from a field. But if you can measure with XRF or with some sort of georadar metals in soil, it's also sometimes a good indicator of any other type of pollutants. So that could be an approach to sort of look for the thing that is easiest to measure, and then go more in depth with soil samples or water samples.
And with any of these spectroscopic methods, you do need to build a model based on the lab measurements. So you do your lab measurements, and then you do your LIBS or your spectroscopy, and then you build a model saying, this is what I want to measure. Does this spectrum vary with this chemical compound that I'm looking for? And then it finds the correlation between those two, and you build a model that way. But you always have matrix effects where all the other chemicals that you don't want to measure are always going to be there interfering with your measurements. So you have to build a model that picks out the variation based on a lab measurement. So it does require both, and then you can check in different periods that your lab measurements are corresponding with your field measurements to make sure that that's stable.
Another rather easy approach is to look at plants, because even if these areas are not cultivated, there are weeds growing up. When the season comes, there will be plants, and you can see patterns in growth. If there is something toxic there, you can look at imagery taken by drones or by rovers or even flyover pictures, and you can see areas of reduced growth. You can probably see things like hydrocarbons are not easily infiltrated into soil, so they will have a signature which is on the soil surface. Metals will also stay to a certain degree on the surface, while other pollutants might infiltrate and disappear from sort of surface scannings. But plants, like archaeological findings, are sometimes done just by looking at very low sunlight. You can see height differences in plants. This is, of course, with the crops that have even height, but I think imagery based on you can do probably
3D,
near
you can do 3D imaging. You can do LiDAR or stereo.
Yeah,
imaging.
LiDAR with different wavelengths. I mean, plants get more or less green or blue according to whether they are lacking or some nutrients, or if they are intoxicated by some pollutant. So this is also an approach, just looking at color images. So.
Yeah, I had a point to that, because after you've cleaned up agricultural field that's been bombed, and you've seen some photos where one field has maybe had like hundreds of craters. After it's cleaned up, it's safe again. The farmer is obviously going to be very keen to, as quickly as possible, start to produce something in the field again. And I was also thinking, can you actually use maybe some of the plants after you've done a cleanup, look at the vegetation there, do some sampling of the vegetation actually to find out, is it healthy enough or to grow food here? Because I think it's clear that it's none of these fields are going to be completely pristine anytime soon. So like try and have a more focus on the food production more than like, there's obviously going to be heavy metals, but when is it okay to grow food again, and what kind of food can they grow?
Maybe I can slightly comment on that. In Ukraine, of course, the priority, not just for us, but I think the Ukrainian government and I think the broader European community is to have food production again. is to enable the land to be used again. How and whether it should be used, that's a question that we, as an organization, can't really answer for the time being, other than the bits of research that we've done, taking very limited samples, as you've seen with Kristen's presentation. But that being said, yes, it is a strategic priority that farmers are able to return to their land. Whether that's being used then as a indicator of the land still being contaminated by by various chemicals, I think that is something worth looking at. But then, of course, there's also the various ethical aspects that we also have to take into account. And I think that's maybe, at least for NPA, maybe that's slightly beyond our scope, but it's something that we can still raise. That being said, though, we're hoping that a lot of these technologies can be used beyond just Ukraine. And just to give an example, and perhaps following up with a question to Marian from that example, is yes, in Ukraine the conflict is very fresh, so a lot of the stuff is laid on the ground. You will have some vegetation growth, but then there won't be as much vegetation growth. Well, it's been 3 years in some areas, so that might depend. But in a lot of the other countries that we're working in, when we're working in more than 20 countries around the world doing similar type of work, it's been 20, 30, in some cases 50, 60 years since the conflict, and we're still doing the clearance in these areas. And so then all of these areas are completely overgrown with vegetation, for example. So perhaps looking at maybe not necessarily Ukraine, but in those instances whether you have a baseline to compare to, maybe that would be one possible avenue where we might not necessarily be the experts on, but we can help facilitate that. So maybe a follow-up question to Marian then is looking at the multi-sensor capabilities that are now available, especially when you're talking about scanning large areas with drones and so on. Is the capability now to an extent where you can actually go through vegetation or determine just based on vegetation cover, and even subsurface types of contamination, whether it's solid materials that have been leaching into the ground? How deep are we talking about in terms of the technology that's out?
So the spectroscopy, light-based methods and XRF, they're surface measurements. So you will measure just the top layer of whatever is at the top, whether it's vegetation or soil. And then radar will penetrate and go in depth and do slices. But you can do with light. With plants you can do multiple reflections, and you'll get information from several leaves. For example, it'll go through the leaves. But then it would have to have some kind of chemical signature that we need to pick up on, and it could be color, it could be pigmentation, but it could also be something else. And then spectroscopy can help with that because the wavelengths will give you different shapes in the spectrum depending on what you're measuring. But for penetration, it would be radar. That's the method to go deeper into the soil. And then with light methods and X-ray, it's mostly the XRF, is surface type measurements.
Thank you. In the interest of time, I'm going to have 2 more questions. I've received one question here with me, and I think I want to save that question for last. But perhaps, I think, Nima, you had your hand up, so I'll go with your question first.
Thank you.
Would you? Yeah.
Thank you. Basically, I haven't read your entire report which you presented from BA's side, but just curious, have you done any research on the type of weapons that has been used both from the Ukraine side and by the Russian side? So artillery, mines, cluster ammunition, and the origin of those weapons. Because we do know that during war, when your arsenal starts getting empty, you buy weapons from everywhere. And not everywhere use simple TNT in their high explosive shells. Some places, as we know, like in Japan, for example, during World War, they used picric acid, which was much more complicated and also basically also harmful than TNT. Do you have that kind of information available?
Maybe I can answer that. I can see that you're an EOD nerd, Nima. Yeah. So in terms of the weapons that are used and the ammunition that is used, yes, to a certain degree. It wasn't NPA's research, but it came from various channels, open source intelligence being one of them. But the comprehensive kind of book that we're using now, at least in the mine action sector, comes from Geneva International Center for Humanitarian Demining, GICHD, and they have a list of all the various types of ordnance that have been used. But that's just the names and models. Whether they belong to, let's say, a North Korean style, 152 millimeter, which may or may not have TNT, that I'm not sure of. And that's purely me speaking from an EOD point of view. From a scientific sense, I'm not qualified to answer that question. I don't know, Kristen, if we have any information on various chemical compositions of ordnance types.
No, not as Norwegian people say, but I'm sure that there are research being done on that. But I think also maybe would be interesting to hear from Forsvarsbygg as well in relation to if there are general in most conflicts are similar weapons and munitions being used, and that which meaning you could, if you do research, that you can look for similar pollution across countries and conflicts as well.
I can have a comment on that. Of course, white phosphorus is banned in Norway. It's not used here, but what's been used other countries we have no control of. And you mentioned picric acid as a sort of compound that was been researched during the Second World War in Norway. Also, it's very unstable, explosive. So it was an accident, the Raufoss ammunition fabric at that time and during the Second World War, and they couldn't handle it, so they dumped everything into Mjøsa, which is now been monitoring on that sort of explosive. So, but what they've been using there, I don't know. But if they've been using it, it's a very poisonous compound, picric acid, as an explosive. That we know for sure. Yeah.
So maybe the takeaway from that is there's still a lot to study. Even though we might know, the types of ammunition that are being used, we still don't have any clear idea what the chemical composition is from the factory. So I hope that answers your question, at least in Ukraine. But going to the last question then, I think it's very relevant for everyone, is how can we empower the Ukrainian people with all this knowledge? And this is an open question to everyone here. And that would be, I think, how we can think about when we pursue a project like this, because at the end of the day, it is for the beneficiaries, for the people of Ukraine. So, anyone would like to volunteer?
How you can empower?
How can we empower the Ukrainian people with all this knowledge?
Yeah, well, I think making knowledge about the work that is being done available, making it not so complicated and difficult to understand. Contamination is it's like chemistry. It can be very complex, but it can also be made quite understandable for the public, and having available information and class education on what's been going on maybe will help them feel that there is a solution on the way, and that they can also help out with this big project of cleaning up, and that they can contribute because it does make a big difference if you can help out your own country, I think, in important aspects of repairing these wounds from the war.
I also have a comment. I've worked on a lot of applied research projects, and one challenge that is often found is that you don't actually listen to what the end user needs. Yeah. You decide that maybe this is what they should do or have, and actually involving them in defining the problem, defining what it is they need, how they would like to use it. The farmers know what they want as well and what they would like. So I think getting them involved in defining the scope of this project is critical to make sure that we solve something that they need solving, instead of what we feel needs solving.
Kristen.
I think also, as I touched upon in addition to what's been said, what I touched upon in my presentation as well, the need to integrate this into recovery processes and post-war reconstruction, and for the communities to be aware and also have a certain degree of knowledge, at least feel that this is being considered. And I think it's very important for people to also have that, have the knowledge, but also have the safety that the community they live in is actually safe, that it's safe to drink the water, or if it's unsafe, that they have an alternative, but that they know to a certain degree. I guess the challenge in Ukraine is that it's a huge issue, and there's so much needed to be done. But I think compared to other conflicts, I think this is the conflict where this issue has been really on the top of the agenda from the international community, for Ukrainian national authorities as well, and is incorporated into their reconstruction plan as well, like green recovery and reducing the impact and pollution from the war. So I hope that this will be integrated in recovery and reconstruction. But I think also from today that we need to collaborate more across sectors as well. From now on and in the future. And this is even more important in the case of Ukraine.
Thank you. On that note, I was going to give closing remarks, but I think those were perfect closing remarks. So thank you for everyone for helping this lively discussion. So maybe on that note, I would like to thank Anna for helping us organize this event. Of course, the great folks here at Tekna and FTU, Reshad as well. He's been behind the scenes working on making this event possible, so couldn't have done this without you. And of course, our wonderful donor, Innovation Norway, Teresa, thank you so much. And thank you everyone for attending.